The mirror equation for a spherical mirror relates how far an object placed from the mirror is to the distance that its corresponding image will be from the mirror. The equation says 1 over f, where f is the focal length of the mirror, equals 1 over SO, where SO is the distance between the object and the mirror, plus 1 over SI, where SI is the distance from the image to the mirror. Now in the case shown here, all three of these variables, focal length, object distance, and image distance, are positive. The focus is on the same side as the object within the curvature of the mirror, so the focal length is positive. And in this case, the reflected rays actually meet up at the image. Since the reflected rays actually converge there, that makes the image real. So in this case, the value of SI, the image distance, is positive. Here, the light rays don't actually converge, and they only appear to converge behind the mirror and originate at some point where the image is formed virtually. In the case of a virtual image, the value of SI in this equation, the image distance, is defined as negative. A convex mirror, as shown here, only produces virtual images. So in the case of a convex mirror, SI is always going to be a negative number. In addition, for a convex mirror, since the focus is on the opposite side as the object, for a convex mirror, the focal length is defined as negative. An image's magnification gives the ratio of the size of the image to the size of an object, and it relates the two heights of the object, HI for the image and HO for the object. Magnification is defined as the ratio of HI over HO. And this ratio can be determined by just using the ratio of the distances between the image to the mirror and the object to the mirror. Now this formula uses absolute value, since virtual images can have a negative value of SI. Magnification just gives a ratio of the size of the image to the object without referring to whether it's inverted or upright in AP Physics. But in the case of real images, all of them are inverted. In the case of virtual images, all of them are upright. The first example here gives a concave mirror with a focal length of 10 centimeters, and an object that has a height of 5 centimeters is placed a distance of 15 from the mirror. So the mirror equation, 1 over focal length equals 1 over object distance plus 1 over image distance. In this case, that means 1 over 10 equals 1 over 15 plus 1 over SI. Subtracting 1 over 15 from both sides gives 1 over 30 equals 1 over SI. So SI, the image distance, is going to be 30 centimeters. Now as for the size, I'm going to use the magnification formula. So the magnification is the height of the image, which I'm looking for, over the height of the object, which is given. Now for the magnification, it's going to be the same as the ratio of the image distance to the object distance. So the image height over the object height of 5 equals the image distance of 30 over the object distance of 15. So this means that the magnification in this case is 2, and then the height of the image is going to be twice the object's, which is 10 centimeters. So I have an image that is a little bit beyond the center over here, and it's going to be twice as big as the object. I know that the image is inverted because I got a positive image distance, which means the image is real, which means for a mirror it's on the same side of the mirror as the object. The next example is also about a concave mirror. In this case, the object has a height of 6 centimeters and is a distance of 5 centimeters from the mirror. This time, the image is virtual because it's on the opposite side of the mirror as the object, and it's a distance of 15 centimeters from the mirror, and since it's virtual, this distance is negative. So to solve for focal length, 1 over the focal length equals 1 over the object distance of 5, plus 1 over the image distance of negative 15. So 1 over the focal length equals 1/5 minus 1/15, which is 2 over 15. So in this case, the focal length is 7.5 centimeters. This question also asks for magnification, which is defined as the image height over the object height. Now, while I could solve for the image height here, I'm not going to, because I'm going to use the fact that the magnification is also equal to the ratio of the distances. So in this case, it's absolute value of negative 15 over 5. And here I get a magnification of 3. For a concave mirror, the location of the object gives information. For a concave mirror, the location of an object determines how big the image is going to be. If the object is placed beyond the center of curvature, it's going to produce a smaller image than the object is, and that image will be inverted and real. Between the center and focus, the image is going to become enlarged. However, it's still inverted, and it's still a real image. Between the focal length and the mirror itself, the image will still be enlarged, but in this case, it'll be an upright image, which means that it's virtual. And this shows how changing the object distance for a concave mirror affects the size of the image. And here's a look at convex mirrors. For convex mirrors, the image is always virtual and smaller in size. The next example deals with a convex mirror with an object placed 12 centimeters from the mirror. In this case, because it's a concave mirror, the focal length of 8 is negative. So in this case, the mirror equation is going to say 1 over the focal length of negative 8 equals 1 over the object distance of 12 plus 1 over the image distance. Negative 1 over 8 minus 1/12 is negative 5 over 24. So the image distance is negative 24 over 5, which is negative 4.8 centimeters. Now, because this image distance is negative, I know it's a virtual image, which means it's on the opposite side of the mirror as the object. And I also know, because 4.8 is less than the object distance of 12, that this image is going to be smaller than the object. So the magnification here is going to be absolute value of the image distance of negative 4.8 over the object distance of 12, which gives a magnification of 0.4.